Pode começar? Okay. Okay, so let's continue to do the lectures. So as I said yesterday, now we are going to shift a bit from closed to open system dynamics. And this is where we will keep for the next lectures as well to exploit this new phenomena that can occur in these open systems dynamics. And specifically, we are focused on this class of maps that was derived in the 70s by Gorini, Kozavakovsky, Sudarshan, and Lindblad, that it's what we usually call as just Lindbladian master equation. Okay, so just to give first some motivation or some outline of what will be our lecture today. The main goal is going to be the derivation of this specific map. What are the main properties of this thing? What are some main consequences as well? But then let's just say in simple words, what do I mean by open quantum systems? Open quantum system is just that you're not looking anymore, as we did yesterday, for the full system dynamics or the dynamical map for all of the degrees of freedom of my system, but I'm just interested in a sub-region of it and in deriving an effective map or effective differential equation for this part here. So any system that's in contact to an external environment is what we call, in a general form, as an open system. Okay? And of course, that understanding the effects of the contact or the coupling of my system to an environment, it's a very, very old subject since the beginning of quantum mechanics, right? So we have our quantum systems that at some point it loses all of the coherence, all of the superpositions, all of the quantum properties, and this is because essentially it's contact to this environment that causes a lot of the coherence, and we lose all of these properties. So the understanding of the loss of this coherence or the loss of the information in my quantum subsystem, it's a subject from a long time ago, but still also a very topic, hot topic that we can address. And especially nowadays because of all of the quantum applications for quantum mechanics, right? So we want that our subsystem to be not in contact in general to the environment, or if it is in contact to the environment, that is not so detrimental for the quantum properties of my subsystem. So especially in quantum information and computation community, if you want to build your quantum computer that make operations for a long, long time, and then you can overcome some classical tasks, you need to understand very well what are the effects of this environment on your logical qubits in your computer. Okay? But then recently, so the left one is about the coherence, the loss of the coherence. It's actually a big review of how this comes from, how the coherence recovers the classical word or the classical properties of the system. And of course, some more recent discussion on this. It's quite nice. I mean, I suggest for everybody to take at least reading the abstract, I would say. It's very, very useful. And the right one is more related to applications in quantum information and computation. So how, even though we have the coherence, we have these detrimental effects, we could still try to manipulate in a good way our logical qubits or qubits in the computer. But then, I mean, recently, not recently, I would say, a few decades ago, there is a big change of paradigm with respect to the effects of this environment on my quantum system. So here, I mean, actually, I would say more these two references here. This one is Petruccioni. I don't know if anybody works here with open system, but if you work with open system, this is like the Bible of open systems formulas. But these other two, and especially this more recent one here by Rosario Fazio, Jonathan Killian, Leonardo Mads, and Marcus Quiro, it's an amazing review of the status, the recent status of the discussion. And it exploits how this change of paradigm can be very good for for this type of dynamics. So on one side, yeah? So this last one, now it's submitted as a review for SciPost recently. The first one is a book, yeah. So it's the theory of open quantum system, if I recall correctly, the title of the book. Okay, well, this is an amazing book, okay. This recent review, it's, let me say, it's a very nice complementary to the book because it gives the more recent updates and related to this change of paradigm as well. Because on one side, we somehow always see the environment as some detrimental for the quantum effects, right? But then recently, I mean, actually, on the other side, we can also try to exploit this competition that arrives in open system, that is, your internal dynamics is unitary, right? Your spins, your microscopic constituents, they have some unitary dynamics that is competed with a frustrating dissipative environment, okay? Usually this frustration, it leads to the coherence, but it can also lead to some new dynamical regimes or some new phenomena. And this change of paradigms or this other side of the coin is what people have been exploiting in the recent years. And there are some very interesting phenomena that arise on this other side of the coins. Actually, you can find some very rich phenomenology when you look for a system that has this type of unitary and dissipative competition that becomes even nicer when you go for a system with many body interactions. And this is going to be the goal of my lecture, these lectures actually. Okay, so you can find from this competition, this non-trivial competition, some new phases of matter, or some new dynamical regimes that are, of course, not allowed at equilibrium, because here we are intrinsically at a non-equilibrium conditions. Some new critical phenomena that are induced because of dissipation. So dissipation can also induce some phase transitions, and this is a dissipation measurement induced only phase transition. So this is unique from this type of environment. And of course, you can also use the dissipation to manipulate your quantum system in a good way as well. So actually, you can even perform some universal quantum computation by just changing how your environment is acting on your quantum system. So this is really a big change of paradigm, right? Instead of detrimental, we can do what we always want for quantum information processing, okay? Of course, that when we say that we have an open system, a major requirement or a major challenge is how we describe the dynamics. And this is a very non-trivial task, right? So essentially, we want to find a way to describe the dynamics of only my system, and I don't really care about the environment degrees of freedom. It's something like trace out all of the environment degrees of freedom, and I want to find the corresponding map for my system dynamics. Yes? In principle, it could be everything here. But when I go to Markovian dynamics, it's going to be thermal bath, okay? Because in some sense, this could be the most general thing that you can imagine, but this is very hard to deal if it's not a thermal bath there. Okay. But even being in a thermal bath, you can still exploit in a good way. That's the main idea. Okay. Okay, so in general, of course, this is not going to be just a unitary time evolution. As I'm going to discuss, you can always find some completely positive trace preserved maps or some operator sum representation, what we call also as Krauss decomposition for the corresponding dynamics. Even though these maps, they are also not easy to represent and to deal, and they are very challenging. And then we go for this specific class of maps, that is what we call as Markovian maps, that was derived, yeah, that's true, in the 70s by GKSL equation, okay? So actually these were some independent derivations of the same master equation. This is very interesting. And also by a delay of just 1 month between each other. On one side, there was Kozakovsky, Sudarshan, and Gorini. On the other side, Lindblad. And they derive the same type of master equation here. Okay. And the goal then of this lecture is to make the mathematical derivation of this specific equation. So you see this equation here, it says that the dynamics of my density matrix, or the dynamics of my quantum system, it has essentially two main terms, right? The first term is driven by a Hamiltonian. It's just the Schrödinger equation here. It's just a unitary or a coherent equation. But then you have these messy terms that appear here that are some jump operators that we call these L operators that act on my system, minus some anti-commutator of L dagger L to my system. And these new terms here, they arrive because of the dissipation, effective action of dissipation on my quantum system when I trace out the dissipation out, okay? And then essentially you have when we call unitary versus dissipative competition, is because these two terms here, they do not agree on what they want for the system. While one term might be trying to align your spins along a specific direction, the other one may be trying to decay all of the spins as a spontaneous decay, and then you have, depending on which one is the stronger one, you have some different phenomena that appears there, especially when the spins, they also interact in the middle of all of this process, okay? Okay, so then let's go for the mathematical calculations. Where's the light? Okay. So let's start by setting the mathematical grounds. We are going to call our system by S. And address a Hermitian space, Hilbert space, as HS for my system. I'm going to have my environment. So let me say that my letter is terrible. If it's not easy to understand, just let me know as well. Okay, and then we have an environment with a specific Hilbert space for my environment. And we are always going to consider this type of situation that I have a system here with the corresponding Hamiltonian. I have the environment with corresponding Hilbert space. And all of this is within my system plus environment that now lives in the tensor product with the Hilbert space. And I'm going to represent all of this by a specific Hamiltonian that I call the SE Hamiltonian, okay? So essentially, this full Hamiltonian, it is going to have some terms that depends only on the system degrees of freedom, also some terms that depends only on my environment degrees of freedom, and of course, some interactions between the system and environment. Okay, so this is S degrees of freedom only, environment degrees of freedom only, and this is the interacting term between them. And the general goal here is, given that I have a system, environment, initial state, we know that the system is going to evolve with time according to the Schrödinger equation, right? This is what we know. So essentially, the system at any time t is just given by our unitary dynamics. Where the unitary is nothing more than the exponential of my full interacting Hamiltonian as E times T, okay? But the goal here, or the challenge here, is that we are not going to be interested in how the environment degrees of freedom evolves, but we just want to know how the system degrees of freedom evolves, okay? So we do essentially what we call as a partial trace over the environment degrees of freedom, where I integrate out all of my possibilities in the environment. And what I will be saying, essentially at the end of the day, is just the effective system dynamics, okay? The goal is not all the time we need to make these two paths, but we want just to understand if there is an effective map that drives my initial state or any initial state to the corresponding final time without having to pass through all of the environment properties, okay? So you want to find what we call as a map that acts in my density matrix from an initial time to a final time that can describe essentially what is the output here, such that my final state is equal just the application of this effective map into my initial state configuration, okay? Of course that this map, it can be very general, but it at least needs to be physical. And this is what we call as the map needs to be completely positive and trace preserving, because it needs to map physical states into physical states, of course, okay? So when we say that the map is physical, we essentially say that it's a completely positive and trace preserving, in the sense that if I act this map on my initial state, or any state, this is always going to lead into a final state that has positive semi-definite properties, okay? Yes? Yes, yes. So essentially, we want to trace out any information about the environment, okay? So we want a map that acts only in the system Hilbert space, okay? So when I say here that I have an effective map, it's going to act only in the reduced state also of the system only, okay? Okay, so for this map to be physical map, it needs to preserve the positivity of my density matrix. Essentially, this output state here, if you look for the distribution of probabilities, it needs to be positive, right? And this essentially is given by this condition that this density matrix, the output one, it's always semi-definite positive. Yeah? If the map is physical, it needs to be respected. Because one condition for your state to be a quantum state or a physical state is this twofold condition, right? So a quantum state is always any density matrix that has the trace equal 1, okay? So if you sum all of the possibilities of the different probabilities of the state is equal 1, because we have the probabilistic interpretation of quantum mechanics. And essentially, it means that this is a positive semi-definite matrix, okay? So this defines any density matrix or any quantum system, okay? If you don't have this, it means that you have some lack of information about what's there, and it's not really a physical state that you're describing there. So any quantum map should preserve these two properties here, okay? That's essentially what I'm writing here. So also, if you look for the trace of the output state over any state, it needs always to be equal 1, okay? So trace preserving comes directly from this property. Positivity comes directly from this property, but we always say that we have a completely positive. Why we say completely? Because we also want that the environment to be a physical state as well, okay? So the complete property, it's some further properties for the map that if you attach any external system to my input here, the system is still going to map physical states to physical states, as we expect for the environment degrees of freedom here, okay? But we don't need to pay so much attention for this property in general. Okay, so how we derive first general forms for this map here. we can make the rough path first, that is really making the shredding dynamics, and seeing what's the output when I make the partial trace, and observing what's the corresponding method. So we know that the system at times t is essentially the partial trace over my environment of my evolved state, that is this guy here. So it's just the unitary dynamics at times t. Let me put t also here. Acting on my, hello? Okay, acting on my initial state, t dagger, okay. And at this point, I'm going just to make a first assumption, or a first condition, that I assume that initially my system and my environment, they are decoupled from each other. As the dynamics starts to go, they can be correlated to each other, but they can always prepare somehow the system and environment in a way that they do not really see each other. So I assume that initially, rho initial is equal just some initial state for my state, and my environment is also in any external state, okay? And then I put here that is just in this specific configuration, and this is also quite general. So in principle, you can say that, okay, but this could be also a mixed state, a completely thermal state, but I can always write a thermal state as a pure state if I increase a bit more the dimension of my environment, okay? It is what we call as a purification of any density matrix. We can always say that a pure state is just a mixed state is just a pure state in an enlarged environment. It is what we have also here, right? So you could consider that this guy here is just a mixed state in a smaller one, or a mixed state is just a pure one if we enlarge a bit more the environment. Just to say that this is a pretty general condition, apart from the fact that we assume that they are completely uncorrelated at the initial time. So then if we substitute this to our equation, we have here the unitary at times t, and then we have my initial state for my system, tensor product, 0, 0 for my environment, ut dagger, okay? And what's essentially a mathematical procedure of making a partial trace? A partial trace is when we make an unbiased average over all of the degrees of freedom of my environment. So I can write down the mathematical partial trace over my environment if I just choose a specific basis and I make these internal products or the internal expectation values over all of my environment degrees of freedom, okay? And then I act with this with my cat, and I act with this, with Brian on the left and cat on the right over all of the input state, okay? So this is going to just repeat, ut, rho system, initial, tensor product, 0, 0 over the environment, and then I act everything again. So I do nothing in my system, but I check the properties of my environment in an unbiased way, because I'm just summing over all of the possibilities in these degrees of freedom, okay? And then you see that essentially is what we want, right? Because when you make a bracket over any operator, over any space, we are essentially getting a matrix or a space and turning into a number, okay? We are making a contraction over all of my environment degrees of freedom into just an average expectation value of what is going on there, okay? So, I'm sorry, please correct me if there is many typos. There will be many typos. Oh, yeah, that's true. Thank you again. In the last line. Okay. So as you see, it's going to have a lot of typos. It's just to see if you're paying attention or not. Okay. Yeah. So this last step here is how we do mathematically a partial trace over some degrees of freedom, right? And a partial trace is just making, you assume that you have not a complete information of what is going on there, and then you need to make some unbiased probability of all of the possibilities, okay? When you make an unbiased probability distribution is when you look for the expectation value of all of the possibilities. So you're making a lot of brackets over what is going on in my environment, this degree of freedom. But since I want to make an unbiased estimation, I need to sum over all of the elements in my environment degrees of freedom. Okay, this is more or less the definition of, not more or less, this is the definition of a partial trace. Okay, when we don't know what's the information there, and we want to understand what's the description here, if I don't have the information there. So just to be a bit more clear, the next step, we are going just to expand all of this in a slightly different form, where I have the identity here, the expectation value of my environment here. And then I can just rewrite this thing here as the identity, again, applied to my system, and the cat applied to my environment, okay? And then the system becomes alone here again. And then we write essentially the same, but with the bra notation for the right parts. So then we have the bra on my environment. I'm sorry, the identity first, on my system, tensor product of bra in my environment, U dagger, identity of my system, and the basis E of my environment. Is it possible to see from the top there? Okay. Okay, then essentially what we have a big operator acting on the left and acting on the right over my initial state, right? And this is essentially what we wanted. We want to understand what is a super operator, a map that acts only in my initial state. And then we call all of this big operator here as our effective operator sum decomposition. You see that here, essentially, when we make the bracket here of this term, we are essentially contracting all of the degrees of freedom of my unitary to only system degrees of freedom, okay? So this first step here is essentially what we do here, that makes a contraction of environment degrees of freedom. And then essentially we call this whole operator that is left here as the Krauss operator, or sometimes also operator sum decomposition, and we call everything here as the Krauss operator mk that acts at time t. Okay. In summary, what we have is that now my system degrees of freedom at times t can be just written by the sum over all of these operators, mk at times t, that acts in my initial state, okay, mk dagger. And this is essentially the effective map at mapping from initial state, from initial time to final time in my system initial degrees of freedom, okay? And there is a whole theory behind these decompositions here, in the sense that any completely positive trace preserving map can always be written by this specific form here, where these are called the Krauss operators, and the number of Krauss operators also can always be below than the maximum degrees of freedom of my system, so there is a lot of interesting properties. But in essence, any quantum map can be written in a cross decomposition in this form. One S only. Okay. And let's say that, yeah. It's in the previous slide. Okay, yeah, so it's on the right here. So, no, but yeah, because cross decomposition, it could be for any map. So when you restrict your map to be Markovian, then you go for the Lindblad-like equation. But if your system is not Markovian, let me say, then it can still be written in this form. So in some sense, the Lindbladian can also be written in this form here, because this is the general form. But it's usually simpler to write in that other specific way. Okay. You need two assumptions. We're going to get there. One is the Markovian one, and the other one is the continuity of your dynamical equations. Okay, it needs to be continuous during all of your dynamics. These two properties only is enough to recover all of the Lindbladian equation. Not, and of course, yes. But Markovian is also assuming this kind of thing here. So essentially, when we say Markovian, we are assuming that this preserves during all of the evolution, okay? Essentially, you can have some time dependence on the system only, but the environment is going to just be frozen in some sense. It's not really affected by the system degrees of freedom. Okay? So mathematically, if you assume Markovianity and continuity, all of these physical implications, they are implicit there. Okay, so we have always this cross decomposition, and one very important property of these cross operators is that they need to act for all of the space of my system degrees of freedom. So, I'm sorry, yes? Yes, that's a good question, because usually it's operator that is some linear operator. Operator is a linear operation on vectors in my Hilbert space, okay? So it maps vectors to another vectors. This is a linear operator. Now a super operator, it maps operators to another operators, okay? So it does not act only on vectors, but it can act on density matrix to another density matrix, okay? So it's another level of complexity or how you can act in your Hilbert space. Okay. Essentially, let me put, this is a good point, because usually a linear operator is something, let me call K, that acts on vectors and maps into new vectors, right? Now we want to act not only on pure states, but we also want to act on mixed states or any basis for my whole Hilbert-Schmidt space. So then we have what we call as superoperators. And then we have this notation of a map, let me say in this way, that acts not on vectors, but it can act on any basis for any linear operator in my Hilbert space. So then this is going to act here, and it's going to map, let me say, to a sum of C, ij, ij. Okay? In other words, it can act not only from the left. It sees the left and sees the right and makes all of the manipulation that you want and maps to another linear operator in this space. Okay, an important property for the cross decomposition is that physically we expect, or it's reasonable to expect that these operators here, they can range through all of my Hilbert space, right? So it needs to act on each specific part of my degrees of freedom. So mathematically, it means that this is a completely set in my Hilbert space for the system. In other words, it means that if I look for m dagger k m k, I'm just going to drop the time here just for convenience in the notation, and I sum over this action over all of my cross operators. We can just simply expand this, and this is going to be given by that guy there. So let's do this identity, tensor product of k. Yes. Tensor product of k in my environment, and then I have my unitary at times t. I don't leave this identity and my initial state for the environment. So just for simplicity of notation also, since the identity here is not going to change anything in the operations, I'm just going to drop this, okay, for convenience. So I'm just going to say that these things here is just the k of my environment that is acting in my unitary. Of course, the unitary acting in system environment, degrees of freedom, but I'm just making the contraction here, and we have this expectation value here. So we have this dagger times the same thing without the dagger. So this is essentially this dagger times sum over k times the same thing, k environment, unitary, 0. Okay. Okay. And then when we make the dagger of the first term here, we have just to exchange the ordering. So we have u dagger appearing here, k environment, and then we have the bra of my environment as well, unitary, and the initial state of my environment. Okay. Then we can move this sum to here inside, okay? And then we remember that for any basis, when we make the whole cat bra over all of these bases, this is a complete set of all of my degrees of freedom, and this is essentially equal to the identity, right? So if we make the sum over all of the terms, this is just the identity. And then what is left at the end is just the u dagger times u, unitary matrix. This is equal to the identity again. And then what is left is just the expectation in inner product of the 0 that is equal 1. So at the end of the day, this is just equal to the identity over all of the degrees of freedom of my system. And this is saying that M operators is a complete set. So here is the identity over the environment. Yeah. That's correct. So this one is the identity over the system environment. Okay. So here is the identity over the environment. Here is just the full unitary acting on everything. And then this is the identity over the system environment. But then you make the contraction over the environment one. Exactly. The last one is a number, but what it does is takes the identity of the system environment and just contract to identity of the system only. Okay. Then this is implicit that there is an identity of the system here that I'm just removing for simplicity of notation. But this makes a contraction over all of my system degrees of freedom. Okay. So it maps the identity over the environment to a number. But what is left is the identity over the system. Okay. It's a bit messy also. It's nice to make perhaps some simple example just to see how these contractions appear. But yeah, it's a bit hard. Okay. Okay, why do I say that this is a very important property? Not only because we're saying that the operators, they need to act on all of the degrees of freedom, but also because it gives us a nice physical interpretation for the role or what the map is essentially doing in the effective system description, right? So we have this interesting physical interpretation. And for just a few moments, let us just forget that we have these operators here. We have done everything here. We just assume that I have a system and I have an environment, and I want to make some projective measurements on my environment only, okay? So assume that I have some projective measurements on the environment only, which is just given by these projective operators, right? So in order to have the outcome K for my measurement in the degrees of freedom of my environment is just acting on the system with the identity. I do not change anything in my system. But then I check if my environment is really at this configuration specifically, okay? Everybody is used to this collapse and measurement theory, okay? And then the probability for this to happen here is just the expectation value of this projector over my density matrix, okay? Let me start here. So then it means that if K outcome is measured, it means that my detector had gone to a click in this specific configuration for the environment, and after the click, we know that the system collapsed directly to this specific configuration, right? So after K is being measured, we have a collapse of the wave function, into the corresponding state pk, the state of my system environment at times t times pk dagger. And since the collapse may not be a unitary operation, we always need to do a renormalization of the corresponding final states, okay? And the normalization is just the probability of this guy to happen. This is quantum mechanics, postulates of quantum mechanics on respect to measurements. So essentially, if we want now to describe, again, only the system degrees of freedom, and we don't care about what is happening in the environment degrees of freedom, so then the system at times t, given that K is measured, is just the state at times t. That is essentially the collapsed state, pk rho system environment at times t, pk dagger, over the normalization. And then we don't care about the environment degrees of freedom, and we need to make, again, the partial trace over all of this subspace. Yes, for any initial state, you can have even mixed state. even correlated state as well, you can have always across the composition, okay? But perhaps if you have a correlated state, the cross decomposition is going to be a bit more messy, okay? But essentially, you can follow all of this procedure for any initial state. We are going to be interested here in the specific class of the initial state that is uncorrelated to the environment. That's our only condition here, okay? And in principle, the environment can also be a mixed state, can be a thermal state. All of the things that we're going to derive here, it works equally well, okay? But in principle, any quantum map that is a physical operation that acts in our system, without taking in consideration the other degrees of freedom of the environment that you trace out, it can be written in this cross decomposition form. This is for sure, okay? So just, okay, I'm really late. So, but just to say, I mean, when I say that this is general, you can imagine, let me put just some addendum here. You can imagine that you have an environment that is a mixed state, right? It's Pi, I. Okay, it's not just 0, 0. What I can do is that I can consider a larger environment. So I enlarge my Hilbert space. Now it's E plus some E prime that is of the same size of my initial environment. And I can write down this initial pure state, or this pure state, that is just the sum over Pi, I. Okay? Is it clear to see here? Okay, so I'm just mapping a mixed state in a reduced subspace to a pure state in an enlarged Hilbert space. But of course that if you trace out the enlarged case, you go back to this mixed decomposition, okay? So that's what I'm saying, that when I say that the environment here, it's a pure state, I'm considering that I'm probably enlarging my environment degrees of freedom in such a way that I can describe as a pure state instead of a mixed state. This can always be done, okay? There is not a unique way. You can do in many different forms. The only thing that's important is that how many terms you have here. I'm sorry, the environment needs to be at least the same dimension of the first one. The enlarged one needs to be, because you need to make copies of your system. And of course, this is a highly entangled state as well. So if you think about practical forms, it's going to be a bit hard also. Okay, so if K is measured, we have this guy here. And here it comes because we want the system degrees of freedom only. And here is essentially the collapse of the wave function. And if we expand then, so this is the system given the K is measured at times T. If we expand this, then let me just open a bit this guy. This is going to give us the partial trace over E of the projectors. Let me write down everything directly. So this is the partial trace. Is going to arrive at operators. That is what we have given there at the beginning. The identity over these guys. Yeah, maybe it's better in this way. Let me write down partial trace over the projector. That is equal to the identity of my system. And then I have K over my environment. This guy acting in the dynamics, unitary, initial state, system initially, 0, 0. And then the rest is the repetition, right? The repetition of everything in the rest, with the dagger appearing here. Okay? But then essentially, you see that the procedure that we're doing here is the same procedure that we did in this step here, right? In this step here. When we make the partial trace, we just need to make this unbiased average over all of the input, which is essentially the same input that we have here. It's the same guy that we have here. The only new thing that appears here is that you have a cat operator here, and you have a new bra operator on the right part as well. Okay? But then this is essentially, you're saying that you have the partial trace acting, the cross operators, they are going to appear here again. But then you have acting in my system degrees of freedom, M, K, dagger, but then you have the cat and the bra here, and then you have the cat and the bra operator over my environment degrees of freedom. Is it clear? Perhaps I went too fast, but it's essentially the same calculations if you open down this thing here. So projective operator, it's just this term here, unitary dynamics, this term here, and the rest is the dagger. When you see that these operators here, they are just the cross operator that we have written there. And then this is just the make the bracket. We are going to be left with mk acting in my initial state over mk dagger. And remembering, we always have the normalization of my wave function here. Of normalization and the normalization here as well. Okay? Yes, exactly. So given that you have your system that is evolving, the system environment is evolving, right, according to your unitary dynamics. At some moment, you have done some projective measurement in the environment only, okay? If the K outcome is measurement, yeah, depending on what happens in the environment, it's going to affect the system degrees of freedom. That's the idea. If K is measured on the environment by this projective operator here, the system degrees of freedom, given that K is measured, is just given by this guy here. That's the main thing. Okay? And the normalization here is just the norm of this numerator of my system. It's just the probability of pk to be measured. That is just the trace over mk rho system initial mk dagger. Okay? And out comes the physical interesting interpretation of this guy. Let me erase. Okay, so if the system is coupled to this environment, and the environment is being measured, so there are two possibilities that could be happening here. So if the environment measures these guys here, the system is going to collapse directly to these guys here. Okay? So then if the environment measures a different K, the system is going to collapse to a different K, and so on, right? So if we have the situation that we have continuously monitoring of my environment, then the system is just going to be collapsed into all of these possibilities, right? It probability K into the systems S, K at times T, okay? But now imagine the situation that we have an observed environment. That is essentially, the environment has these projectors there, but it does not explicitly read the information of what collapse has been done or what is the exact state that was measured there. So when I make the description of my system, I also don't have the information of what is the precise K that was measured. And then what I have essentially is just the probability distribution of my system estimates to be each one of them with the corresponding probabilities. Right? So then the description of my system at times t, if I don't have the information of what is the outcome of my projection measurement of the environment is just this pk times the probability of my system to be at times k in the k collapsed state. And then if we just expand this, is very simple. The density matrix at S and K is that last line there. That is just the sum over the Krauss operator acting in my system initially, mk dagger, divided by the probability of this to happen, right? And then we just cancel all of this thing, and we just have essentially the Krauss or the operator sum decomposition appearing here again. Rho initially for my system and mk dagger. That is essentially the CPTP map acting on my initial system. Okay. So this is a very interesting interpretation for what this equation is giving to us, right? This equation is just saying that I can see this thing as I have an environment that probably is trying to make some measurement on what is going on in the system dynamics, but we don't have this information of what is being measured there. If we don't have the information, then I have a poor description of my system degrees only. I just know that with some probabilities, it can be at different collapsed states, okay? In some sense, I'm increasing the entropy of my system description because now I don't know which system has, which outcome has been collapsed, okay? And this is very interesting. Usually we are going to focus, especially for this lecture here, in this case of unobserved environment that we don't have this information. But recently, a lot of works has been done also in the continuously monitoring in the environment. That your system now is being collapsed many times as a stochastic quantum trajectories, and then you have some new phase transitions that appear there, only because you are continuously looking for what are the outcomes that are being done in your environment degrees of freedom, okay? And this is pretty cool, I think. Even though we are going to focus on this, that is also nice. Okay, let's just see a simple example of these things that I think it's going to be very fruitful. So let's just consider a very simple example that we can still handle in the Krauss decomposition form, that just some energy dissipation or some spontaneous decay of a single atom. So imagine that my system now is just one atom that can be in 2 degrees of freedom, either the ground state or some excited level for this atom. And if this atom is in the excited degree of freedom, since it's in contact to a quantized electromagnetic field, and this is going to be our environment, the electromagnetic field, it can be at some decay rate, decays spontaneously and emit a photon to my vacuum or to my electromagnetic field, okay? Then we have an atom acting as a system in our notation, and the electromagnetic field acting as our environment degrees of freedom, such that when this guy decays, it emits a photon, and if I have no photons in my environment degrees of freedom, then I have one excitation to one photon in there, okay? So let me just write down, this is equal to 0. That is just the vacuum of my quantized electromagnetic field, and I can have these excitations in there, okay? And these things could occur with some certain probability P, okay? So the dynamics, essentially, it says to us that if the atom is initially in the ground degrees of freedom, then nothing is going to occur in my degrees of freedom of the electromagnetic field, and this is just going to be constant, right? There is no spontaneous decay to occur in the system, atom and environment. However, if my atom is now in the excited level, then my environment can see or can detect the decay, and then we have with some probability p of this to happen. So probability 1 minus p, nothing occurs. The atom keeps in the excited level. And with probability p, we have the decay occurring. So the atom now goes to the ground state, and we have an excitation over my environment. Okay? So the full unitary that describe this type of dynamics here is very simple. It's just if you have input ground and 0, it just keeps ground and 0, nothing happens. Atom, environment, atom, environment. But then, with probability 1 minus p, you have, if your system is in the excited and no photons, it keeps there. However, if you are with probability p in the excited 0, it can occur a decay to ground and 1. Okay? So as we learned, to obtain the effective description of my system only, I just need to compute the Krauss operators for an effective map. Okay? Then this is very simple to compute, right? The Krauss operator for k is equal 0 is just making the expectation value of 0k over all of my unitary over my initial state of my environment. So let's suppose also that, again, the system environment is initially uncorrelated in this form here, where the environment is initially in the vacuum configuration. To make this guy here is very simple, right? So we just need to make the bracket over 0, 0 on the environment degrees of freedom. And we see that we have one term that appears here that is just left out the ground for our atom degrees of freedom. Also, we have this term here. So we have also square root of 1 minus p times excited. I should have chosen, I think, different E, because it's not E of the environment, it's E of excited in the atom degrees of freedom. Let me call that this is U. I'm going to put explicitly the time depends in the next step. Okay, but it's the probability of U to occur at this moment. Okay. And this is just a very simple matrix that is the ground plus square root of 1 minus p over my environment degrees of freedom. The second Krauss operator is when k is equal 1. Now we have k equal 1 here, the unitary and 0 over my environment, This is not here, this is not here, this is not here. Environment, and environment. And then we see that there is no term that appears here, 0, 0. 0, 0 also will not appear here, but then we have 0, 1 that survives from this last term here, and then it just have square root of p and the ground and excited state for the atom. This is just a matrix like 0, 0, square root of p, 0. Okay? And then my density matrix evolution, given that my system initially is a general state, given that my system initially is a general state, CG, a probability of ground excited, ground, excited. We just have that the state at times t is just this double operator here, right? As time initially, M0 dagger, plus M1 row system initially, and 1 dagger, which is just playing with these elements of my input state here and applying this specific matrix over it. So it's not hard to see that we are going to have something like this, row system over time. When I apply this first term here, that is acting on the diagonals, but also the off diagonals is going to have some terms that is just the multiplication of the first times the second. So then we have the first term is just the CGG times 1, nothing happens. The CEE is going to receive this guy twice, and then we have 1 minus P appearing here, while the off-diagonal elements is just the product of these two guys here. So I have CGE is just the square root of 1 minus P, and CEG the same, square root of 1 minus P. Plus the action of my second term, that is just a decay of the excited to the ground, and then it's just mapping the CE into some ground state configuration, right? Then the second term is just going to give us that 0 on the off-diagonal elements, but what was here in the CE has now been gone to the first term, times the probability of this to happen, that is square root of P, okay? In essence, this gives to us that the final density matrix is CGG plus square root of P times CEE, and then, okay, I'm sorry. Okay, no, that's correct. So CGE square root of 1 minus P, then we have CEE here, 1 minus P, and here is just the complex conjugate, right? Hermitian conjugate. Okay. And to solve the dynamics, we just need to solve that this guy here is going to be increased by some factors that depend on the probability, while these off-diagonal terms, they are going to be decreased by the probability, as we expect, and also the probability of being excited is going to be always decreasing with this spontaneous decay rate, okay? So now just to give a more precise time dependence for this thing here, so just a more precise time dependence, we just write down that the probability of the spontaneous decay to occur is just given by some decay rate that depends how your atom is interacting to this electromagnetic quantized field, times the time that it was interacting to this electromagnetic field, okay? Then we can see explicitly the time dependence on this parameter and how these dynamics evolve, okay? So in this way, if I wait for a time that is just a repetition of this procedure here n times, so n times dt, we just have that my quantum state at times t is going to be described by these guys here. But then what we have is that the first what we have is that the excited probability is just 1 minus the probability of this to occur to the power of n times of this operation has been done, okay? Then we just substitute to put the explicitly the time dependence here is just 1 minus P is equal to the decay rate times the time step to the power of n. If we look for the continuous dynamics, it means that this term here is very, very small, and this is essentially just the Taylor expansion in first order of an exponential thing. So this is just the exponential of minus gamma delta t to the power of n. And n times delta t is just the final time that we want to see. So then you see that the probability of finding your state in the excited mode is just exponentially small with time. Is somehow what we expect, right? Because the system's interacting to this environment, it has some decay at some point, which occurs exponentially fast in the time. We can make the same procedure, for example, for the off-diagonal elements, how the coherence is lost in this procedure. But now we just have that is 1 minus p to the power of n over 2, and we just have n over 2 in the exponential guy here, t over 2. Nevertheless, it says that we lose all of the quantum properties, quantum coherence, exponentially fast in the system, and at the end of the day, we just have the ground state in there. Okay? Good. I don't think that I will have time to finish everything that I have prepared, but there is not a big problem also. I can postpone a bit for tomorrow. But now, this is a very, very simple case that you can still construct the cross operator and make analytically the corresponding evolution, right? But we just have a 1, 2-level system coupled to 1, 2-level environment. This is very, very simple, and we can do everything. In general, this is definitely not the case. And then we need to have some approximations for the class of operations that we are dealing. And here is where we are starting into the Markovian dynamics or the Markovian class for these maps. Okay? So now, in general, what we have is that for any initial system configuration, we saw that we can create a corresponding map that for any final time is just the map acting to my system at the initial time, okay? And this could be done for any other states, right? If I consider some different initial configuration, I could reach some different time at a finite time as well, but it's always going to be given by the same cross operator map, given that the initial condition of uncorrelated is the same. So this is also the corresponding map for final time acting in my initial time. Okay. So now we go for the conditions of Markovian dynamics. The first condition is that we impose that the corresponding map that makes the full dynamics for any initial state, it's continuous. So we impose the condition of continuity for my maps. So of course that this guy is going to be driven by some path, and this other one is going to be driven by perhaps some different paths and so on. But then we are assuming that we want to construct a map that can be acting in each one of these continuous time steps, okay? So this somehow leaves us to the question, if it is possible then to write down this map from the initial state up to the final state as just some continuous decomposition of my map acting along all of my trajectory, okay? So this makes us to make this question, is it possible to write down the full map as starting from 0, and then you just make a small delta step, then you make the corresponding from dt to 2 times dt, and then you continue this up to the final guy, that is t and t minus dt, okay? But this may not always be the case, and let's see why it can always be the case. So the reason is that when we try to impose this property for the continuous dynamics of my map, I'm saying that I can look during all of the trajectory here, and for each infinitesimal time step here in my trajectory, I can write down the corresponding time step for my map, okay? So if I look for my quantum system at times t plus dt, then I'm saying that this is just making the action of my map from times t to times t plus dt over my state at the corresponding time t, okay? And this should be valid for any initial condition and also for any trajectory. So if I decompose also the trajectory of my different initial state, it means that for any time step here, infinitesimal, as rho of s t plus dt is just going to be given by this map of t plus dt acting on it, okay? And then we cover the first initial condition, or the important condition that we gave to derive the cross map, is that the initial state, system, and environment, it needs to be uncorrelated, right? And nothing guarantees that during all of this evolution here, at any finite time, the system remains uncorrelated to my environment. If it does not remain uncorrelated to my environment, I cannot apply the same map or the same cross decomposition for the middle of the path here, okay? So in essence, this map here that makes this middle time step here, it may depend on my system as well, okay? Because in some sense, it was created some correlations between the system and environment, and at this point here, I cannot apply the procedure, and these correlations here can come back to my system at a later time as some kind of backflow of information and affect what is going to happen in the next time steps, okay? And at the same side, this guy here could depend on my initial preparation, okay? So this usually can happen, and this is what we call as a non-Markovian dynamics, when we have that the map for any time step, t plus dt, it may depend on my system historical path. So this can be different from this guy here. In other words, what I'm saying is that during the dynamics of system and environment, they create some type of correlation between them, or some form of information of the system is imprinted in the degrees of freedom of the environment, such that at a later time, this information can come back to my system and then affect what is going on at this later time there. So you see that there is this backflow of information that at a finite time says that the map may be different from this other one, because the form of the initial preparation was done differently, okay? And then what we mean by Markovianity. By Markovianity, we say that there is no this there isn't this backflow of information. The dynamics essentially forgets everything that has done in the past and just look for the future. So the map here will not depend on the initial preparation of your system, rather it's just going to be the same for any initial input, okay? So essentially when we say that we have a Markovian dynamics, we say no memory on the dynamics, on the map. And this is essentially saying that during all of my system environment dynamics, I cannot create any type of correlations between my environment. So I always have an environment at a thermal state, while the system can have some non-trivial dynamics along all of the path, okay? And we will cover then that this becomes an equality instead of inequality. Yeah. So, yeah. So, for example, you can think that at time t, for example, when you make the full dynamics of the system and environment, even though initially the system was uncorrelated to the environment, during the dynamics they create some type of entanglement, some classical relations or anything like this. And then if you look for the full density matrix, it's not exactly equal to the system at time t, tensor producted to the environment at times t, okay? So it means that your system now is entangled, okay? If it is entangled, you still can construct some cross operators, but the cross operators do not necessarily are the same that you have constructed initially, okay? Okay. And this can occur also for your different initial preparation of your system. It can have some different correlations at time t. Tensor product, oh, this is the raw environment at times t. This cannot be the case. And it means that the cross operators might be also different from these cross operators in here. Okay? Essentially, what they're saying that during the dynamics, at times t, they create some type of correlations. Okay? If you look then for some larger times t prime larger than t, it can be that this information is now going back to your system. So it's going to affect what the dynamics is going to be at a later time. So you have somehow the memory of what was the initial preparation that is going to change the movements of a later time. Okay? So then the map, it depends strongly how you prepared and how the correlations between your system and environment evolved. Okay? It's not the same map independent on the input that you give there. Is a bit more clear? Okay? Yeah, okay, yeah. Not always the case. That's the interesting thing. So I would expect that non-Markovian allows more interesting phenomena. That's even true. That's also true. But even in a Markovian type of dynamics, you can still have non-trivial effects there that arise because of this competition of some irreversible or non-memory dynamics to unitary and coherent dynamics that is the internal part of your microscope dynamics. So that's why I think that it is also a change of paradigm, because this is not trivial, right? You expect that if you have Markovianity, it's just losing memory, and then at the end you're getting some trivial states. You have a classical state or something not so good. But that's the point. It's not always the case. And that's why I'm going also to show some examples that's going to be more clear, these things. Yeah, because, so let me just finish here, and at least I finished the Markovianity. That is a direct consequence of this no memory of my map is that now I have some irreversible dynamics, right? I cannot see in the past. So while in general maps, if you have an initial state here and you have a different initial state, each one during dynamics may have some different path, but it may happen that sometimes they are completely indistinguishable to each other, right? And then if you have a non-Markovian that remembers what happened in the past, it can be that here, for my initial preparation in row S, the map acts along this direction here, while for the other one, that not necessarily leads to the same path, but since it remembers all the initial preparation, it can lead to a different next step of my dynamics. Then we have this type of non-trivial dynamics occurring. And it means that we have memory of what is going on in the past. So this is what a non-Markovian dynamics. On the other hand, if we now impose this type of strong condition here, and we have the same situation of two different initial preparations, each one has its different path, but at some point they become completely indistinguishable. At this point then, they need to converge to the same path, okay? So the dynamics that drives the future of my system depends only on the state at the time local configuration, okay? And then we have that all of them converge to the same guy. Okay? In essence, you cannot retrieve the information of your initial preparation. You just lose this information along all of your dynamics, okay? And then we have the map in here, in a Markovian case. That's why usually we also expect, but not always the case, that during a Markovian dynamics, your entropy is always growing and growing, right? Because you are always losing some information of the past of what happened there. But that's not always the case, of course. Okay, we can have the spontaneous decay, for example, that at the end of the day, all of your atoms, they are just in the down configuration, and you have a pure state there as well. And a pure state is, you know for sure what's going on there. There is no uncertainty in your description of the system. Okay. So yeah, so I think that I'm going to stop here because the time is left. In the next talk, we derive from this point the Lindblad master equation. Okay. Any questions? I'm sorry. Yeah, this is a good point also of that you could exploit in a positive form in a Markovian dynamics, right? Because if you engineer some type of Markovian dynamics such that you're just looking for the steady state or for the times going to infinity, and you look for good properties of this guy here, then you don't really care how you prepare your system in the lab, because you know that everybody is going to converge to what you want. This is a good way to exploit that we're going to do also in some examples, right? But that's true. If you have irreversibility in your dynamics or no memory, everybody is going to a fixed point, and it does not depend on how you started the dynamic with. Okay.